Let's continue our talk about system ID, but let's do it for second order systems. So second order systems not only have low and high pass, they have bandpass and notch, but they also have over, under, and critically damped. Over damped, of course, has two real roots, which means two different exponential decays. Critically damped has one repeated root, which shows up in two different exponential decays. One just scaled by 1, and the other one scaled by the pole times t. And then underdamped, we have an exponential decay times a sine wave. These equations you can find these at the Swarthmore site. So anyway, let's just review second order low pass filters. We have a damping factor of 10, that's two real roots, and you can see a pole here and a pole there. And they're separated in this case by quite a distance. This is about 10 kilohertz, and that's about 2 or 3 megahertz. So depending on how you're testing it, you might not even see this pole. And let me point that out. So if I'm doing a step response, this looks almost just like the step response of a first order filter with a single pole at 10 kilohertz. So if we calculated 5 tau or measured 5 tau divided by 5 and took the inverse and scaled it appropriately by 2 pi to get the frequency, we would get about that. You can just see that. Now for critically damped, in fact, that I have found to be reliably what you might call 6 tau. That if I measure how long it takes to get here and divide it by 6 and take the inverse, that's very close to the omega naught. It's much more critical, or it's a lot harder to do for the overdamped case, because when they're equal, when the two poles are getting close to each other, that approximation just doesn't work. And then here for the underdamped response, right, how long does it take to kind of get where it's going? It's really, you have this minus zeta times omega naught. And so in fact, if I measure from here to here and there's only one exponential decay, I can kind of call that this 5 tau-ish type thing. So if I divide that by 5 and take the inverse, I don't get omega naught, I get zeta times omega naught. Now you can actually get zeta from the peak here. In fact, it's relatively straightforward to find what the system is when it's underdamped. The other ones are a little bit harder. So for the high pass, right, we start low and go high, and the green is underdamped, blue critical, and there's my two poles. Now the thing is now in the low pass, it was the low pole or the smaller pole that dominated the response of how long it took to discharge. But notice what happens in this case. It's the higher pole that dominates the discharge. See how quickly it goes for the high pass? The high pass also has this, for the critically damped, it goes below 0 and then comes back up and settles. Right? That's not really underdamped. That's just how the high pass works, because we've got two poles here and they're the inverse of each other. So one is going down, one is going up, but it's the dominant pole that is detecting the edge. And for underdamped, It's just a phase change here instead of positive. But just to go and kind of review, the low pass, right? It's right in here. It's acting like a double integrator. Um, for the critically damped, it's acting like a double integrator up to here. Same with the critically damped, but then of course it behaves quite differently from there. But starts high, goes low. Starts low, goes high. All right, it's acting like a differentiator, double, single differentiator, double up until it stops, double, and then you have this resident peak. So it won't necessarily make the best differential circuit. We have some Desmos links that I'll go into in a little bit. Now, the bandpass. Notice it's attenuating. It's got a high pass part and it's got a low pass part. Now, this can be quite hard to find, but really, if you just take V in and subtract the low pass response and the high pass response, you will get the bandpass response. Because remember, we can think about it in a series RLC circuit. This denominator would be the same. A high pass would have S squared. The low pass would have omega naught squared. The band pass has some S in the middle. And the whole response would be the sum of those three terms. So if I don't know this term, but I know the low and the high, all I have to do is subtract. And I can go from there. Now notice that for the critically damped, the two poles are separated by quite a bit, and it's the lower pole that dominates for the bandpass. You can see that it's taking a long time to discharge. In fact, what it's kind of indicating is that the low pass part of the bandpass is so far away from the high pass that you just can barely even detect it. Now for the critically damped, yep, starts at 0 and goes back to 0, right? Because we're kind of getting rid of the low pass and the high pass. So if the low pass passes DC and the high pass passes AC, right, we're getting rid of the AC here and we're getting rid of the DC here. We'll see that a little bit better, all right? But it's happening right at 100 kilohertz, so it's decaying a lot faster. And then for the critically damped, sure, it's very narrow, but we're getting an oscillation function that, takes a certain amount of time to dissipate. Now, the notch filter, you can almost think of it as backwards, where we have a high and then a low. We have a low pass and then a high, right? Where the cutoff frequency of the low is smaller than the cutoff frequency of the high, where here the cutoff frequency of the high is smaller than the cutoff frequency of the low, which gives us our notch filter where we're trying to get rid of 100 kilohertz in this example. So now when we look, we don't have to rederive it, we just add the low pass and the high pass response. And for the critically damped, yeah, you can see this kind of very quick edge, right? It just comes down and then slowly comes back up to DC, right? So that quick edge is the pole out here, and then the slow rise up to 1 is the pole out here. Now, there's one root at 100 kilohertz, so it happens faster, but you can see that it shoots up to 1, detects the edge, gets rid of something in the middle, and then goes back to DC. And then for the underdamped response, it starts oscillating at 1 and goes to DC. Now let's try to put this together. Um, and I wanted to start with the review of extracting a second order filter response from the Bode plot, creating a model from it, and then verifying it against measured results. So here's a Bode plot of a second order RLC circuit, and I did it. You can see that there's a little noise in the phase, where with the LT spice, it's very perfect. If it's a second order filter, you just pull off omega naught at minus 90 degrees phase and go from there. Right? It's minus 90 because it's obvious that this is a low pass filter. The gain at DC is 1. Since there is this noise in the phase, I'll just use the asymptotic method. I bring out 0, right? And then this purple line, I bring it up and drop it down, and my cutoff frequency is about 350 kilohertz. Then to find zeta, I read off the transfer function at that point, which is about 0.56, solve for zeta, and it's about 0.89. So it's slightly underdamped, right? If this line was lower and hit at 6, then zeta would be about 1 and be critically damped. And if zeta was greater than 1, you'd start to see 2 breaks, right? So because I only see 1 break, yeah, it's going to look critically damped or somewhat underdamped. If this line hit at minus 3 dB, zeta would be 0.707, which is the Butterworth conditions. But notice I wasn't able to get out to a minus 180 degrees because my test equipment, that's about as far as I could get it to test. That's okay. You can still find there was enough data to take a straight line here, straight line there. I only went to 50 hertz. I didn't really go down as low as I do in my LT Spice. So I found the DC gain, omega naught. I found the transfer function at omega naught, and then calculated zeta. So then I made an LT Spice model of that and then plotted it. That's the frequency response. And then came up with an RLC circuit. Originally, I'd put in an 80, 20, and a 10,000 picofarad because that's what the part said. But when I measured it, it wasn't. They didn't match, right? Because the values were off. So what I did is I varied C1 to get the phase to cross at 90 at the same spot. Then I adjusted the R to get the damping coefficient correct. So now you can see in the Bode plot, it's matching fairly well, right? And for this, the transfer function is 1 over LC. That's 1 over LC is omega naught squared. R over L is 2 zeta omega naught, right? Then I went and did the transient response. So I selected the underdamped response, 0.89, 2 pi, 350K. And you can see that this is my behavioral source where I implemented that function, and it matches. And you can just see this little tiny overshoot. I mean, it's just almost undetectable. And you have to look very closely when you measure it as well to see that. So that's great. Now I remember I started with a measured Bode plot, and I wanted to go back and see what it looked like with a step response. And lo and behold, I was very surprised that the output from the function generator, which was a step response when it wasn't connected to anything, then when I connected it to the RLC circuit, it turned into a notch filter, which was surprising. Now, sure, the output can be seen in green, and that still looks like something again, that overshoot is kind of hard to see because it's just barely underdamped. But why is that notch filter there? Right? Because there's the edge, it detected the edge, then it's getting rid of something in the middle, and then it goes back to DC. Right? So, thought about it, pulled my hair out, and realized that the function generator has 50 ohms series resistance. So I changed the circuit, and this FG is function generator out. That's really what's going on in the circuit, right? I mean, that's really what's being fed in. So when I simulated that, well, lo and behold, there was my notch filter, but it didn't make sense. So what I did is I just found the transfer function of that node, which is the sum of these three impedances divided by the sum of the total impedance. And look, you get something kind of interesting where you get a second order denominator, um, but you have all three terms. And usually we only have a middle term, the squared term, or no S term, but I've got all three. How is that a notch filter when it's usually S squared plus the DC term? Well, look at the ratio here. R1 over RL versus R1 plus R series over L. And at mid-band, when we simplify, we get R1 divided by the sum of these two resistances, which is less than 1. Now, the interesting part is, why did the Bode plot work? Well, because when I measured the magnitude, I took the ratio of these two. In my Python programming, I didn't just assume this was always AC1. I just divided this by this, and it worked. Because even though this was going down, it doesn't matter. The output would have gone down by that. That's why I was that's how I got a little bit surprised. So now let's have a quick look at some Desmos plots. So this is overdamped, and we have two poles. I have it at 1.1. There's no reason I can't make that one, but and then I'm having the second pole go back and forth, so it goes out of range, and then it comes back in. If it were to be equal, it would stop working because that'd be critically damped, right? So the red is the low pass, and when this whoop, right, and when that second pole gets really big, you can see so in 1 second there, that the smaller pole is dominating for the low pass. The notch is in blue, and it detects that first edge and then passes the DC. And the orange is the bandpass, where it rejects the low and the high and passes something in between. And let me just try to zoom in. And the black is the high pass, where you can see it detect that edge. But remember, there's two different exponential decays going in opposite directions without a DC offset. So this is not underdamped by any means. It's just the fact that you can actually see the two poles. So I think it's actually a lot easier to find the system when it's a high pass, because you can get the fast and the low poles just by looking at it. Where with the low pass, one pole is much bigger than the other. You might not even be able to see if it's a second order system. And we'll save that there. The critical damped, right now it's just one pole, and I am moving that back and forth. All right, notice it's the band rejects the edge. It also rejects the DC, so it's passing something in the middle. The notch is detecting an edge and detecting DC and rejecting something in the middle. The low rejects all edge and passes DC, and the high pass detects the edge and goes on detecting it until it comes back to zero. So still there is no, the low, the notch, and the band don't have any overshoot. And I guess the thing is this is um, where is it going to settle to zero? Right? It doesn't cross zero more than once. So that's critical or overdamped. Again, if you look at this kind of curve, it can be really hard to tell whether it's over or critically damped. Um, but with a lot of the questions I ask, I'm just asking for things generically, not like from the Bode plot, which you can get pretty exactly. So now we're looking at the underdamped, and that's pretty exciting. Um, let's pause it out here. So zeta is small, so it's going to oscillate quite a bit, but really, um, if I take this value where it pretty much settles to zero, call it 24, and divide that by 5 and take the inverse, that will give me the pole uh, times zeta. All right. For this, the red is the low pass, and it starts low, passes the DC, but it just oscillates a few times before it gets there. The notch in blue um, detects the edge, goes down, but then takes a while to the oscillations have to dampen out, and then it'll pass DC. The band starts off at zero, ends at zero, so it's rejecting the high frequency and the low frequency, and it just takes time to settle out. And now we can really see that the high pass um, is underdamped because it crosses zero more than once. All right, and just settles. Um, so really, um, I think when you can know all four filters, it's pretty helpful because if I hadn't been familiar with the notch filter and I noticed this, I would have been really stumped. Um, that would have really, I would have not known. But since I've been teaching you all, yeah, notch filters are on my mind, and it really jumped out. Now, yeah, getting rid of that um, for the PWM, that would be another lesson.